Hello, my name is Oron. I'm from Registerless Institute of Technology, and I'll be presenting our position of registerless hardware description. We think that the data flow hardware abstraction allows us to separate the design functionality from its constraints by looking at the different implementations of registers and giving them higher abstractions. Let's go to the demo. In this demo, we have the simple moving average design that we saw in the paper. The drawing is here on the bottom, and the implementation in Defiant HDL is here on the top left. We also have instantiation of the design, and we print out its elaborated state at the output here on the right. So the compiler is run and prints out the design. The left implementation is identical to the right elaboration, but that will change now. We now add an addition of a pipelining stage. Automatic pipelining uses some kind of estimation and determines where and what types of pipeline should be added. Now we see that a small difference. An extra pipe stage is added at the output of sum. So it's a two-stage pipe, which means it breaks the sum operation into two parts. But what if the pipelining is wrong, or I want to change it into some kind of other path pipelining? Let's say I want to change it like you see in the drawing here below. I want to add a pipeline stage at S2 and S0. In Defiant, I can easily add it using a pipe construct. Pipe is similar to a prev construct. They look the same, they can have the same argument, which is a step. But their semantics are different. A prev is part of the function. Here I want to add x and x.prev and prev2 and prev3 to get the average window. But a pipe is different. A pipe is just an implementation constraint. So what will happen? Also, here I made a mistake. I manually pipeline just S2 and not S0. What will Defiant do? We see Defiant automatically balance the pipeline by adding a pipe stage after S0. So we essentially very easily created this pipeline here. So we see this printing and this debug mechanism allows us to understand how different stages affect the design. So we add now a compilation stage to a Verilog backend. This is how it affected the design. It added a clock and reset signaling. So we have, in this case, asynchronous reset with the rising edge clock to create the necessary registers to implement this design as a synchronous design. We have extra signaling and inference for the bit accurate carry addition. All of this is composed from several stages under this singles compile command. So let's go on ahead and print the generated file, in this case, a Verilog. So we see something very similar to the output from Defiant, just with synchronous processes and asynchronous process and all this necessary signaling or wiring and inputs and outputs. Again, this is very similar. So we can debug the design just by looking at Defiant code. We don't need to go all the way to the RTL. Maybe we don't know what RTL is. We can just debug the Defiant code at various stages. Just like Verilog code, we can change it to VHDL and get a different output. But the implementation is the same, just some different semantics cause the design to change a little. So here we have a VHDL implementation instead of the Verilog implementation we saw earlier. We also have benefits like bit accuracy compilation checking. So if I made a mistake and forgot to resize, I can see in in the editor here, I can see that the left-hand side argument of the assignment is 16-bit and the right-hand side is 18-bit, and and we don't allow automatic truncation because we can make a mistake. So Defiant is very hard on safety. In conclusion, the demo shows only one of various ways Defiant offers intermediate approach to hardware design and fills the programmability gap between RTL and HLS abstractions. Thank you.